Hello and welcome to the third and last session of our free online workshop, Introduction to Engineering Simulation, hosted by SimScale. My name is Milad, and today we're going to finish our journey through the world of engineering simulation. And I think you actually know the procedure. Before we start to talk about our today's topic, I would like to make sure that everybody can hear me loud and clearly. And therefore, please click the raise your hand button in the case you can hear me loud and clearly. You will find this button in the GoToWebinar control panel, which is the software we are using to deliver the live stream of this webinar. I can't see any hands so far. Oh, now I see the first hand, so everything is working, right? Perfect. By the way, there's also an alternative. You can also listen to the voice of the presenter by using our toll-free audio service numbers. And right now, you will see several of these numbers on your screen. For every country, we have a different toll-free number. And just dial this number and enter the access code you can see on the slide once you're asked. All right, it seems like everything is working from a technical point of view. So let's take a look at our today's agenda. And as you know, this is the third and last session of our workshop series. And on Monday and yesterday, we're focusing on CFD, on fluid flow simulation, as well as on thermal simulation. And today we will finish this journey and talk about the last discipline, which is structural simulation. And again, at the beginning, I will quickly introduce you to the fundamentals and the most basic content of structural simulation. So you will learn basically what structural simulation is, what are the potentials of structural simulation, and where and how can I apply it. And this section will be followed by a short introduction to SimScale and our free cloud-based simulation platform. And finally, we have again prepared a very nice live demonstration for you where we will put you into the seat of an electronic design engineer, and we will together find out how simulation can be used to optimize cooling concept for electronic devices. And we will simulate the heat conduction through the solid parts of the electronics. And finally, again, we have time for a Q&A. One general thing. Yesterday, some people wrote on the chat that they already heard some part of the presentation. And basically, it's true. We decided to make this session independently so that you don't necessarily need to attend the first and the second session to understand what we will discuss today. But this also means, as a consequence of this, that some parts of the fundamentals have to be repeated in every webinar. And in the case you already listened to the webinar yesterday or the webinar on Monday, especially at the first 10-15 minutes of the presentation, might some slides or images will seem to be familiar for you. All right, so let's get started. And just in the case you have a question, please write it into our question toolbox, and I will try to answer immediately to this question or latest during the Q&A. Great, so let's start to talk about the fundamentals of thermal simulation. Of structural simulation, sorry. And first of all, we have to understand what structural simulation basically is. And again, structural simulation, as the word structural and simulation are indicating, is about performing virtual experiments which are able to predict like how a solid body is impacted by a physical load, which can be, for example, a force, a pressure, or also a temperature. And structural simulation allows us to investigate this for static phenomena, dynamic phenomena, and even for, let's say, frequency-dependent phenomena. And this is a big picture. But what does it mean? On this slide, you can see several examples for simulations, for FEA simulations. so-called, which are also called structural simulations. It's a synonym, and it's a really a very wide bandwidth of different applications in physics. So, for example, if you just take a look on the applications on the slides, so what you can see here, for example, is a static structural simulation of a container loading station. And we basically calculated the displacement and bending of this steel structure based on loads we applied, and we can predict how much will be the bending, we can predict which stress will occur and where will we have the maximum stress, and based on this we can decide if the design is robust enough or not. And this is maybe the let's say most usual kind of application where FEA or structural simulation is used for. But you can also expand it. For example, this simulation shows a pipe which is transporting, let's say, hot oil or hot fluid, and here you can see basically here we can see which internal loads and stresses are created by this external thermal loads, and we can even predict where and why exactly this pipe system will crack. We can also simulate very large deformations. For example, here we have a simulation of a deep hollow process of a pipe, and the simulation contains both. It contains the tool as well as the hollow material, and we can really predict what will be the final shape of the hollowed material and which stresses will occur. Yes, and we can also do dynamic simulation, like here where we simulated like the forces and stresses in a skull head bone based on the force of an impact. And the simulation, for example, was used to optimize the design of head protection devices. And as you see, there are a lot of applications. And basically, FEA or structural simulation can be divided in three different kind of analysis types. And basically, one thing is structural simulation, and there we can simulate everything which is related to external forces and how they will impact the stresses inside the body or a design. And here we are not limited only to static, but we can also simulate dynamic phenomena. Like here we simulated the stresses in a camshaft assembly. And based on the kinematics of the engine, we were able to provide boundary conditions as well as kinematic constraints, and this gave us exactly information about how forces are transferred within this assembly, but also it can give us information about the maximum stresses that will occur inside the material of the assembly. And this can basically also be extended to so-called thermal or thermostructure simulation. And there we basically use two simulations. First of all, we do a thermal simulation of the heat transfer inside the solid body, considering the conduction effects, and then this temperature field is used automatically as a boundary condition to calculate displacement and forces. And let's say the third type of simulation is everything which is related to model simulations, where we're not interested actually like in stresses mainly, but we're interested in characteristic frequencies or something like that for model effects, like in this simulation where we have actually a camshaft, and we are simulating like let's say for which frequencies the risk is very high for failure. And I see I have some questions already. First of all, Omka wants to know if vibration analysis comes under structural analysis or it's different. Vibration analysis is basically another word for modal analysis. but this is something which is basically a structural analysis, but it's a very special way of analysis since we are not considering a static or just a dynamic simulation, but a modal one. Right, and now again, I would like to very briefly talk with you about, let's say, the theory or the principle of structural simulation or finite element analysis. And again, we won't dive too much into details, but at least you should have a rough idea of what the computer codes are doing with your input. And so basically what FEA is doing is quite simple. And just take a look at this geometry. And let's say we want to simulate the stress or predict the stress distribution and the displacement inside this metal hook when we apply here a defined load. And if you think about it, there's not an analytic solution which we can use. There's nothing like a formula which we can just use to calculate this. But for some other cases, for very simple cases, there are analytic formulations. And just imagine, the simplest example is a spring. If you have a linear spring, you have an analytic relation which gives you the displacement depending on the stiffness of the spring and the external load. And based on this, you can calculate everything else like stresses and strains, etc. And when we do FEA, the basic idea is that we have a complex shape or a complex problem that we cannot mathematically describe or not solve the equation. So instead of considering this complex system, we will reassemble it from very simple shapes. And for these simple shapes, there are numerical approaches how to describe and calculate the relation between force, stiffness, and displacement. And so what we do is we take our continuum model, which has an infinite number of DOFs, which is, let's say, our real-world model, and transfer this into an artificial discretized model with a finite number of degrees of freedom. And in the end of the day, we transfer our continuous domain into a discretized domain made of simple geometric shapes, which we call elements. And in the end of the day, we later consider one of the every of these elements as a finite small piece of structure. And the nodes between these elements are like the boundary of the elements and fastening them together. And in the end of the day, this enables us or enables an engineer to predict or to calculate what will happen for even very complex structures just by remodeling it based on these finite elements. And that's the reason why structural simulation is often also called finite element analysis, because this mathematical method is called finite element analysis or finite element method. Right, and now let's shed some light on it, and let's take a very simple example. Let's say this is our FEA model, and we're dividing, and this is very similar to CFD, by the way, and the simulation type we talked about the last 2 days. And basically what we are doing is we have this bar which we want to calculate, and we are dividing this bar into 2 sections, 2 one-dimensional finite elements. And this is our main relation. And for every FEA simulation, this is or for every structural FEA simulation, this is our principal relation. It says that the displacement of the system is equal to the product of stiffness and external force. And this should you remember you on the general formulation for the relation between force, stiffness, and displacement in a one-dimensional elastic spring. And in the end of the day, what we do, we just calculate approximate solution for every element. And if you take a close look here, you can see like the solution. And so we have a force or called P acting here, and this is the displacement in this direction. And you can see the blue one is representing the analytic solution for this simple beam case, and the red one the FEA solution. As you see, the FEA calculates only a solution for between or for the nodes connecting these elements, which means that I only have a linear or maybe a quadratic interpolation between that support points. And this is very important because if I have, let's say, a more complex geometry or a more complex, say, a more complex load case, let me just show it to you. Just imagine, can I change the color to blue? Yes, just imagine it would look like this. Then we would need to use another discretization and you put more elements here to resolve this. And that's basically your job as a FEA engineer or as an engineer using simulation. You have to decide where in the model you need which local accuracy. And I hope that now some things becomes clearer and that you really see that there is, let's say, that there are a lot of things which are common between all simulation types. So the general principle is basically the same, independently if you're interested in CFD or FEA. Then there is the next question by Ray. Would you say that CFD is an offshoot of solid FEA principle except it's exclusively for fluids? Ray, that's a very, very good question. Actually, you can't give a general answer to this question. So, and maybe that gives me an example which I hope will make some things more clear. If you think about it, fluid flow simulation is called often CFD, which stands for computational fluid dynamics. And structural simulation is often called FEA, which stands for finite element analysis. And basically, here we're mixing up different things because FEA is a method for numerically solve this governing equations, and you can even do CFD or fluid flow simulations with FEA principles, but usually use some other little bit different methodologies to do fluid flow simulation. So in some cases you're right. You basically can derivate CFD from FEA simulations, but for example, in our SimScale platform, we're using the so-called finite volume method for CFD. And if you're interested in that, Ray, I can recommend you really take a look at our free CFD Masterclass workshop series, which you will find also on YouTube. And there we are also talking about the difference, the exact difference between CFD and FEA. Great. So one final thing. I think we talked about the last 2 days, so let's not go too much into details. But why should you care about simulation, especially about structural simulation? Well, the reasons are basically the same why you should care for fluid flow simulation or thermal simulation. Simulation allows you to virtually experiment your designs and explore different design solutions at a very early stage of your development process. And which is maybe the most important thing, there is no additional cost for operating the test rig or building a prototype, and it usually gives you the possibility to do very fundamental analysis at the very early product stage. Sometimes our customers or people using simulation even don't have the final design they want to build, but they already start with some rough sketch to do simulations, and this is how simulation can help you to create products faster and cheaper. Okay, there's the next question by Ray about the difference of in accuracy of results between FEM versus accurate methods. And I think, Ray, when you talk about accurate methods, you're referring to what we call analytic methods. And yeah, let's take a look again at the slide. So there are two differences. First of all, methods like FEA or CFD are numerically, which means that they don't calculate from a mathematic perspective the exact solution, but they try to find a solution which is matching as good as possible. And that's the very first big change or difference. And another difference is that usually when you do this accurate method, or how I would call it analytic methods, your result is a function, which means, for example, you really get a function for the stress distribution inside your body depending on the coordinates. While using this numerical methods, you only have a solution for defined points. So basically, it's a question of accuracy. And a lot of people have a big misconception on this. They think that simulation actually should 100% replace physical testing, and that's not true. There are still some things which are easier to find out with physical testing than when using a simulation. For example, everywhere you just want to have a very, very exact number. Sometimes it's easier to do practical tests, but wherever you want to improve something, understand something, and where you're mainly interested in differences between several designs, simulation is a quicker and better tool. All right, so now let's take a very quick look at the SimScale platform. And yes, to put it in a nutshell, as I mentioned, simulation gives you a lot of great possibilities. And actually, simulation was invented at the same time like CAD. But if you take a look at the left chart, which is representing industrial adoption for 3 different technologies, for 2D CAD, 3D CAD, and simulation, it becomes obvious that today just a fraction of engineers is using simulation. And there are several reasons. One of the reasons, or let's say the 3 most important reasons in our point of view are, first of all, the so-called access barrier, which means that all these traditional simulation tools need a lot of infrastructure in the background to be used. And this makes it very complex for small companies or companies who just have a limited demand on simulation for a limited time to find a business case where in the end of the day they can afford it. And usually big companies which are mainly using simulation have own departments just focusing on providing the infrastructure which is necessary to run simulations. Another reason is what we call the budget barrier. Traditional simulation tools are very, very expensive, so you can expect at least to spend 20, 30, 40,000 euro upfront just before you have run your very first simulation case. So buying hardware, buying software, and you also have a lot of high annual fixed expenses for software maintenance and training. And finally, the maybe most important reason is what we call the know-how barrier. All the old simulation tools like Nastra and ANSYS, they were designed mainly for simulation specialists and experts, and they require not of specific know-how because they were developed from the perspective of a simulation specialist. And that's the reason why especially small companies and small businesses, they don't want, and they also can afford to have a simulation engineer who's just taking care of simulations. They need a solution where actually the engineer or designer is using simulation to improve the design on his own. And again, there's a question, and this time by Charles. I think Charles already was quite active yesterday and Monday. Great to see that you like our offer. And he wants to know if our software capabilities compare with existing software such as ANSYS, Neston, and COMSOL. Charles, thank you for this question. I really appreciate that question. I want to be honest to you. For sure, we don't have exactly all the same features like ANSYS, Neston, and COMSOL. Especially ANSYS is a company with several thousand of employees and developers, and that's not our aim. But what I can say is that really the most important analytic types are all covered by SimScale. And this is, I think, relates also to our business model and our philosophy. Our aim, and that's the reason why this company was founded 5 years ago by students, was that we wanted to make simulation accessible to all those engineers, to this big majority of 95% of engineers and designers who don't have access to simulation right now. And therefore, we all the time when we decide which new feature we will introduce, for example, we really focus on the need of the big market. And if you're interested in to know more details, Charles, please specify your question, so then it's easier to discuss it if we can compare, let's say, for example, the CFD capabilities or the structured simulation capabilities. And for sure, you can also free to reach out to my colleagues from our user support and sales team, which can exactly give you an overview about the differences in capabilities between SimScale and other competitors. But what you should keep in mind all the time is that SimScale is much cheaper, and we provide you with a package including everything. But now let's talk about that. So what is SimScale? And a lot of you know it already, but to put it in a nutshell, This company was founded because the founders are really shocked by the very low number of engineers using simulation, and the idea was, what can we do to make simulation available to everyone? And the idea was to introduce the very first cloud-based simulation platform, and that is what we're doing today. We've developed and we are running SimScale, the free and cloud-based simulation platform. And SimScale is basically a fully fledged 3D interactive simulation environment which runs in a standard web browser. And you don't need to buy any dedicated hardware or to download or install any software. You just need a standard web browser internet connection to get access to unlimited simulation capabilities via your web browser. And everything is in the cloud, which means that you don't need to care about computational time, and the platform is never using the local resources of your computer. And we don't only change the way simulation can be accessed, but also the pricing model behind it. So SimScale is a freemium pricing model, which means you can use all our capabilities completely for free, and in return your simulations will become public, part of our public simulation library where other people can use them as a template. And if you need privacy for your projects, we also offer tailored commercial plans where you get the opportunity to create private projects, and there we offer tailored plans based on your needs. And finally, SimScale is designed for everyone. So special, it was really a very important aspect of designing SimScale that it should be used by the engineers and designers themselves. And this is also very important, let's say, USP of SimScale, so that it's more than just a cloud platform. It's in the end the ecosystem where people, technology, and content meets. And I've talked a lot about SimScale, so finally, what can you do with SimScale? We basically support three major disciplines of simulation, including solid mechanics simulation or structural simulation, FEA, fluid dynamic simulation. And solid dynamic simulation is focusing on everything where solid bodies are involved, while fluid dynamics focus on everything where we have fluid substance involved. And we also have thermodynamic simulation or thermal simulation, which can basically be both, and which is used for simulating everything where heat transfer is involved. And finally, we also have some more advanced simulation types like particle phenomena simulation, which can, for example, be used for optimizing bulk material transport, etc. But now I've talked a lot again about SimScale and what we're doing, and now let's get started with our today demo. Right, so and today we will focus on structural simulation. And we will precisely talk about thermostructural simulation. And before I show you what we're going to do today, let me just give you a brief introduction. So as you may notice, the number of electronic devices is increasing from day to day. And today, every one of us has a bunch of devices in his pocket or in his bag, which include electronics and batteries. And especially if for very small devices, it's really mandatory to minimize the chip temperatures. And the big problem is that everywhere where you have passive cooling, where you basically don't have a fan or air exchange with the surrounding of air, you are very limited regarding your design parameters. So the only thing you can change are conduction paths, and isolations, and the materials you use. And when you use a weak design, this can really end in a catastrophe. And on the slide, you just see two of consequences for bad designed electronic enclosurements. For example, an overheated battery in a cell phone or the overheated machine equipment. And yes. And as I mentioned, this sealed electronic enclosure design is quite challenging. And the big problem is that in contrast to some other, let's say, cooling problems, you only can use the conduction. So only the heat transfers through the solid. And then you have different possibilities or different options to control how the heat is transferred and removed from your electronic device. And some of them are cheaper and some of them are more expensive. And maybe one thing everybody of you know are external fins and heat sinks, which are basically used in every desktop computer, where we have this heat sink on the processor, and some let's say more advanced gaming computers even have this more complex constructions where you even have like kind of heat sinks with fins plus a special heat pipe here. But there are also a possibility of using special thermal interface material like the silicon polymers, which have amazing isolation capabilities for both electricity and heat. And for sure you can also use greases or adhesives, which are often combined with heat sinks or special thermoelectric modules. And our job is today, imagine, is to optimize the sealed electronic enclosure. And again, this is a case which is inspired by one of our real-world customers who is designing electronic devices. And basically this is how it works. So we have this simplified PCB board, and on this board we have 3 different silicon chips. And this is this board with the chips is enclosed by this sealed housing, and as you can see, it's sealed, so no air can leave the inside of the ceiling or enter the inside of the ceiling. And we have an ambient temperature of 27 degrees, and we have following a power applied on these chips. And we have some design constraints which we can't change. So we are not allowed to use active cooling because this device is going to be used to control a plant where actually it would be too dangerous to have active cooling. The enclosure is also sealed, and we cannot change the dimension of the box. And basically also the chip temperature. And our job is to make sure that in the end of the day, the maximum chip temperature and the maximum enclosure temperature does not exceed a defined value. And for this, the first thing we want to do is to run a simulation to understand what is the initial state, and based on that results we can think about which strategy and which components we can use to optimize the heat transfer, like heat sinks, heat pipes, etc. And now we have basically again 2 possibilities to run the simulation. The first one is a complex one, which is called a CHT simulation, and we briefly talked about it yesterday. Because if you think about it, inside this enclosure, we still have air, which means that we have again both convection and conduction. But since this air cannot leave, the convective effect will be quite low compared to the conductive effects. But if you want to do it hyper-realistic, we basically have to consider both. We have to consider how the airflow around these chips and around the PCB board is changing the temperature field, and we have to calculate how the temperature field is changing the flow field. And this kind of coupled simulation is what we call conjugated heat transfer, which covers both convection and conduction, and it takes a lot of time to set it up compared to other simulation types, and it's slower, but it's much more accurate. And much more, it's very important because it really depends on what's your aim. For most of the cases, you don't need this very high level of accuracy, and there you can basically apply a convection and use it as a boundary condition, and you will only simulate the conduction, which is much faster but a little bit less accurate than doing the CHT. And today we will focus on approach B. If you imagine, yesterday we focused on a pure convection simulation. Today we will focus on this pure conduction or structural simulation. And what will we do? So first of all, we going to import the CAD model of our assembly on SimScale. We are going to mesh it, so we are going to tell our solver later where we need which kind of local accuracy. And once we've meshed the assembly, we can set up the simulation. So we will define boundary condition, which kind of materials we used, etc. And finally, when we've set up the simulation, we will calculate the simulation results and we can analyze them in our online post-processor. So let's switch to the SimScale platform. And here I have a project, including already the geometry. Let me just open the project. Let me see if there's some questions in the meantime. Yes, again, some questions. Okay, I will answer them later. So again, this is our SimScale platform, and as you know, everything here is cloud-based and happening in our web browser. And you can upload your own geometries using our geometry upload, and we support different file formats like STEP, and IGES and STL, but also some native formats like SolidWorks, Autodesk, and Rhino. And in the future, we will add more and more new native data formats. And yes, when you upload the geometry, it can take around maybe 1 minute depending on internet connection. And once the CAD model was uploaded, you can view it in our 3D viewer. So this is our CAD model. This is the enclosure of our model. Remove just the, and we have different height modes, select modes. So we have different solids. I can, for example, just, what I did now, I just hide it, the whole enclosure. And here you can see like I have different versions of geometry, and this is our initial version without any heatsink or similar. Right, and this is our geometry. And the next step we have to measure it. And now think about it. Since we are interested in the conduction only, we only need to mesh the material, so the solid part. And if you would be interested in the convection, we would need also at least to mesh the air inside. However, creating a new mesh is quite easy. And let me just take one of the meshes which are already finished. This one. And as you can see, you basically just have to select the geometry you want to mesh. Then you just add a mesh operation, in our case TAT dominant. For structural simulations, we only support TAT mesh. And here you just have to say, you can choose automatic sizing. So you just have to say what is your desired mesh fineness. You have to say how, to define how many courses you want to use, and you can define some manual refinements, which we use to refine the heat sinks and the bodies of the chips. And then you go. Meshing took around 15 to 20 minutes. And this is the finished mesh. And the great thing is we can even take a look inside the mesh. So let me just give me 1 second. Okay, and we just have to move this. Click on apply. And this will generate a clip through the mesh. And this can take some time, sorry, because unfortunately using the webinar software together with SimScale sometimes makes my internet connection quite slow. However, so let's wait until it loads, and in the meantime, this was basically our pre-processing. So we prepared the geometry for meshing, and now we are going to set up the actual simulation. And it's still loading. Let's take a look at this at a later stage. Right. However, now we need to create a simulation. Again, I've prepared a simulation and let's now just quickly go through it. So just to show it, at the beginning you create a new simulation and then again you are asked what kind of simulation you want to run. In our case, we do a solid mechanics simulation and it's a thermostructure simulation, which is this is how we divide it, and we basically have a heat transfer simulation, and that's a big difference because heat transfer only includes the heat transfer, while thermomechanical includes heat transfer plus stresses created by the heat. And then you already see some examples you can use to get started with, like this thermal analysis of this PCB or this dual-stage thermoelectric plate. However, and once you choose an analysis type, this tree will pop up and will guide you through all steps. So first of all, you have to define contacts, which say like how the parts are connected and how they're interacting. Then you define the materials for different parts. And finally, you add the heat flux, heat source and this process source and run the simulation. And again, here we used several processors. And this simulation took like 1 hour on 16 computing cores. And then you can take a look at the results, which I will load right now. Okay, so we have some questions. I will try to answer some of them. So the next question is again by Ray. And he asks, I still use basic FEA beam type stress analysis software in my daily work for complex plant piping. Then I zoom in and investigate certain areas with full FEA software when my beams analysis results shown any constant. Is it possible that with this approach I can totally miss local areas that can fail in real world, or should I go straight into full-blown FEA but could end up very expensive or a huge fight to manage? Ray, again, you're the guy for the good questions. You should join for all our webinars. I think you really describe a very important trade-off. And I'm quite sure for some applications, let's say this classic way of using beam models or beam type stress analysis software is really good. And if you, for example, have let's say very simple shapes, it's a good way to go with it. But however, the big disadvantage is that in every design there are some parts which cannot be simplified by beams, and there you will really miss what is happening in the real world and miss local hotspots and local areas with high stress. And what we suggest our customers is that you can still use your old analytic tools to predict where you think there could be a high load, and then you can use this as a starting point to identify those parts where you should run, let's say, a fully fledged FEA simulation. And I hope that answered your question. If you want to discuss it more in detail, please send an email to me on mmurphy@simscale.com and I will connect you to my right colleague. All right, in the meantime, our simulation result loaded. This is a different simulation where we already have the heat sinks on site, and then, you know, here we can like take a look at temperature distribution, at the heat flux, I have to scale a little bit my color map, and you can do clips and slices through the material and so on and so on. All right, now we have 20 minutes or 50 minutes remaining, and so the final is to do the post-processing, to analyze the results and try to understand what is happening. All right, so I have did some post-processing before and prepared some stuff. So let's take a look at the results of the initial design without any heat sink. So this is for approach, what we called approach A. This is our CHT simulation, the fully fledged one, where we have both. And here you can actually see the streamlines of the air flowing inside the enclosure and the surface temperature of the chips and the PCB board. And now let's make a cut section view. So now where the streamlines are, we replace them by a second cut above, a little bit above of our surfaces. Now we can see again the local velocities. And as you see, we have like dead areas here where the flow is not moving. And everywhere where the air is not moving or moving very slowly, we won't have a very good heat transfer. And you can see that, for example, here, where we have this high velocity areas, we will have some good cooling. But here, for example, we can directly see that this high area of fast air, or this area of fast air, is not placed very good. And it would be better if both of them would be more in the middle. Now let's take a look at the velocity vectors in this plane, which we can also visualize. And now you get really a good understanding for what is happening. So basically we have like a big eddy here, this one, and another big eddy. And that's how the air is rotating like all the time inside this enclosure. And if we now compare it, so on both sides you can see the still the same CHD simulation, and the left clips. In both cases, we're representing the temperature on the surface of the board, and on the left side, these cuts are showing the local flow velocity, and on the right side, they're showing the local temperature. And yeah, you can really see like that we have these high temperature areas here and here, and even here in the middle. So there is a temperature just basically too hot. And this is also related to the flow field. And I also told you that for a lot of cases, the simplified version, just doing, instead of CHT, this conductive simulation is good enough. And I think these images are proving what I'm saying. So here we have the same geometry, the same loads. The only difference is that the left image is showing the result for a fully flat CHT simulation, which is more complex. And on the right side, we have the more simple conduction simulation. And if you compare the maximum temperature, it's quite similar. We're talking about a difference of 0.2 degree. And if you take a look at the temperature distribution on the surface of the PCB board, it looks quite different on the first view, but it's related mainly to the colors. But if you take a deeper look, it's quite similar. So we have this chip, the very right chip is very hot. Here we have this hot center, and it's still quite the same. And I hope that this convinced you that for a lot of cases, this simplified simulation is good enough. And the red means high value and blue a low value, by the way, because Godwin is asking. So red here means a high temperature and blue means a low temperature. However, we then only used the approach B, the simplified approach, for iterative design improvements. And here you can see the actual temperature distribution on this chip. This is representing the max chip temperature for chip 1, 2, and 3. And this red line is representing the maximum temperature which is allowed for this design. And you can see that everywhere we are above. So basically our limit should be somewhere here, but we are nearly over everywhere above. So what can we do? And now we will just test 3 different designs. One design is our initial design without any heat sinks, and we have a second design where we add Cooper heat sink, then a third design where we have Cooper heat sinks and a heat pipe plus silicone thermal pads. And by the way, this is the most expensive solution, while this is the cheapest, and this is something between. And now we just performed the same simulations, what means we just uploaded. That's a great thing about SimScale. You can basically just upload a new geometry and change copy your mesh project, change the base geometry, and just with 2 or 3 clicks, you set up a new simulation or a version of the simulation for a little bit changed geometry, which is really helping a lot. And now just take a look at this images which are comparing the different designs. So here we can see the temperature on the surface. And it becomes obvious once we use this heat sinks that we have a massive drop in a chip temperature, not only in the direct near of the chip or on the chip, but also around the chip. Because here most of the heat is like traveling through the board, and since the conductivity of the between heatsink and chip and also inside the heatsink is so good, with design 2 using the heatsink, a lot of temperature is now also transferred through the housing, which is what we want actually. Now we can also compare the heat flux, which we can analyze, and we can really see like how adding this heat sinks is increasing the heat flux, especially on the upper side of the housing and of the chips. And we can also compare temperature between design 2 and design 3. So here we have, in addition, also this. We have first this heat pipe on the chip, and then we have the heat sink, and then we have even lower temperatures. If you compare it with here, everything gets light green, and the heat flux really increases, especially here in the area of the heat pipe. And if we do a final result composition, again, this is our chart, and now you can see like that we're able to decrease the max temperature below the limit everywhere and reduce it by around 20%. But the very important thing is that the simulation proved to us that we don't necessarily need the very important heat pipe. And if you wrap it up, so at the end of the day, our customer needs around 2 hours of manual time to prepare the simulation, which includes cleaning the geometry in the CAD system, uploading, defining all the settings, and 3 hours of computing time, which means it takes 3 hours until the results are available, and he needs to spend 60 core hours, which means that the overall cost for the simulation based on your plan is maybe 100-200 euros. And in return, we saved a lot of time because there was no need to create a physical prototype. We saved a lot of costs because we identified which is the most effective cooling solution, and we got confidence in our design. Yes, and yes, that's basically it. And I hope you really enjoyed our presentation today. And now, in the case there are some questions I have not answered, or some questions you have not asked, just write them and we can discuss them during the Q&A. And yes, since this was the final session, so you will receive an email from us. Sorry, because I told you maybe something different yesterday, which includes all links to all 3 sessions and the recordings, to some material to get started, some course material, some step-by-step tutorials to run your own simulation, and a link to a quiz. And by submitting this quiz, you can qualify for a free certificate of participation. Great, it seems like I answered all your questions. And yes, I would like to thank you all. If you have other questions, you can also reach out to me using my email address. And yes, I hope you enjoyed it. Have a nice week and see you soon. Bye.